Hi, my name is Gabrielle Taylor. I'm going to be doing homework 1 part C. So it says derive a time-dependent material and energy balance equation of a CSTR. Describe, then code solve a time-dependent with the concentration and temperature profiles for the CSTR when the coolant of temperature Tc is increased from to 305 Kelvin at time 0. So, and then we have our stuff they give us. So let's draw this out. So first thing that we're going to do is, this is a CSTR, but this is also an overflow CSTR. So we have a tank like this, and we have some constant stir bar in there. And then we have a flow coming out on the top and a flow coming in, right? And then this also has a cooling jacket. So there's a cooling jacket around this. And the flow coming into this is called our TC, right? So then we have a flow coming in to our tank, right? Our CSTR. So that is going to be called a Q in, right? And then also, what we have is a concentration. So this is a reaction that's happening, and there's going to be an initial concentration going into the tank. So we have a Ca in. And then inside the tank, since this is at steady state, which is a constant stir, that means that it's going to be an equal concentration in this. So it's going to be called a Ca. And since this has an equal concentration in the tank, this is also going to lead us to that what's leaving the tank is going to be the same concentration into the tank, right? But what's coming into the tank is different. So the CAN is different from your Ca, which the Ca is in the tank and leaving the tank, right? And so after this, we need to know a couple things about our problem. This is a first order reaction. So first order reaction is your rate constant times your K, and then times your Ca, which is your concentration, right? So after this, we don't know what our K is, so we have to define an equation for that. So our K is going to be equal to K naught times the xp, so to the exponent of negative activation energy because this is an exothermic reaction, so this is releasing heat, over your rate constant times your T, so times temperature. So that is what's going to help us with this. Now the next thing that we know is the concentration is changing in this, right? The concentration is going to be changing over time, depending on our flow rate and our volume. Our volume is not going to be changing because this is an overflow tank, so that's going to give us a consistent volume. So we know that our concentration and our volume are dependent on each other as well. So we can have our equation as volume times the differential change of the concentration divided by the differential change in time, right? And so this is going to be, so if we think about this, what is our concentration going to be multiplied by? Our flow rate. So one thing about our flow rate is, our flow rate in is going to equal our flow rate out. So Q in is going to equal Q out. So we are just going to keep it as Q. So this is going to be as Q instead of Q in and Q out. So it's Q. So we have our flow rates, and then we have a change in concentration. So it's going to be a Ca minus Ca in. So that change in concentration, right? And then we're going to subtract this by our volume times our rate the rate of reaction rate, which is our Ra. So that is just our K times Ca. So then when we divide this by our V, we're just going to get dCA, so the differential change in the concentration divided by our differential time, times our flow rate divided by our volume, times the change in concentration from Ca minus Can, minus our rate of reaction, which is just K times Ca. Okay, so after this, what we can do is we need to do a heat transfer. So since there's a cooling jacket on this around our stir tank, and this is an exothermic reaction, we're going to have some heat transfer between it from the area, right? So the area around the heating jacket is going to have heat transfer. So the heat transfer, we are going to call it as a U, right? And since this is in respect to the area of where that is touching our CSCR, it's going to be area. And the temperature changes. So the temperature that's in the tank is going to be subtracted by the temperature of the cooling, right? So T minus Tc. So that is going to be our heat transfer. So next thing that we want to do is a mass balance of all of this, right? So to get this in mass, what we need to do is we need to multiply by our rho, so our density of our material, times the volume of the material that it has, and then we have our heat capacity. And then this is going to give us the change in temperature over the change in time, right? So the first thing that we want to do is we know we're going to have the temperature that's in our tank. The temperature that is in our tank is rho times our heat capacity, and then this is going to have, before this, this is like, so the heat of transfer is coming in, but it also is affected by our flow rate, right? So our density, our flow rate, and then our heat capacity. And so then this is going to be subtracted by our T coming in minus our T. And then we're going to do is now we can subtract that heat transfer, right? So now it's UA times T minus TC. And then we were talking about how this is an exothermic reaction because I have a negative up here, right? So since this is an exothermic reaction, we're going to need a heat of reaction, right? So we have a minus our heat of reaction, and our heat of reaction is going to be negative because this is an exothermic reaction, right? So negative heat of reaction, heat, and then we're going to multiply this by our rate of reaction. The thing about this, since we have that rate of reaction, we also need to know how is that heat changing in the rate of the reaction, but also the volume. We want to account for all of it, not one instant. We want to do all of it, so we will need to multiply this by our volume. And let me rewrite this to make it look a little cleaner. So it's going to be VKCA. Okay. So now this we can use to code and then find two different types of, so we can find two different relationships between this, which is the change in concentration and the change in temperature, because these are they have a relationship between each other. And so we'll see that when we plot this. Okay, thank you. I'm doing the coding portion of part C. Before we get to the coding portion of part C, I wanted to talk about our change in concentration equation that I did. So in the change in concentration equation, it was the change in concentration over the change in time equals our flow rate divided by our volume. And then this is the part where I made a mistake. So I said it's CA. It's actually CAN minus CA. So that was flipped. So that is going to change what I previously said. So just as preface, because we're going to put the correct equation into this, into the coding. So that was a mistake I made. So let's continue to do our coding portion. So I imported the library from GitHub. So let's import, the first thing is our starting point stuff. So our Q is 100. We have our CA in. So our concentration coming in is 1, and our T, I'll just do T in, is 350, and then I have our volume is going to be equal to 100, our rho is going to be equal to 1,000. Our C, so our heat capacity, is going to equal 0.239. Our negative heat of reaction, because this is an exothermic reaction, is 5e to the fourth. Our ER is going to be 8,750. Our K naught is going to be equal to 7.2 e to the 10th. Our UA is going to be equal to 5 t e to the fourth. And then we're going to have our initial TC at steady state. And then our C. Ooh, something happened. Okay. Is equal to is equal to 300. Our CA steady state is going to be equal to 0.5, and then our T at steady state is going to equal 3.5. Okay, so let's, oh, and then we want a Tn for this, so our time end is going to be 10. Okay, so the first thing that we want to do is we are going to derive our right-hand side. So define our right-hand side, and then these are given by our time and a vector, right? So what we are wanting to do is, the problem is asking for the relationship between the concentration and temperature profiles of this CSDR. So what values are we wanting to get is going to be based off of our C, our concentration, and our temperature. These are what we're trying to figure out. These are our variables, right? So V for the vector, not the volume, to make sure you do that. So next thing that we need is, so the temperature of the coolant was increased from TC to 305. So we have to put that in there as well. And then our first equation is going to be to find our K. So K naught times MP dot XP. And so the equation is the negative, so we have to put negative, right? Negative E divided by RT. So ER is what we already have, so we don't have to divide by R because it's already divided, but we do have to divide by T. Okay. So next, what we have to do is we are going to do our change in concentration. Just like when I said that my equation in the first had a little mistake, so we are going to really emphasize that right now. So it's going to be our Q, our flow rate, times, so we're going to be multiplying this by CAN minus CA divided by our volume minus, and then we were minusing this by our K times our CA. I don't want to keep that under there. Okay, so that is the updated equation. So that's that, to give you kind of a visual of what it's supposed to look like. Okay, and then we have our D. So the next thing we have, so we have our change in concentration. Now we need our change in temperature, right? So let's do that equation. So it's first, let's put this all in parentheses. So rho times our Q times our heat capacity, right? And then we had our T minus our Tn. And then we subtracted this by our UA times our T minus our TC. Minus, right? So that's our heat transfer. Now we have to do the heat of reaction. So I'm just going to add this because the negatives cancel out. This is a negative number. It's going to be a negative. that will just flip the sign to be positive. So I'm just going to keep it positive just because it will save me putting in that negative sign. So we have our negative heated reaction. We're going to be multiplying this by our volume, and then times our K times our concentration. Concentration, the C there. Then we want to divide this, and we wanted to divide this by our mass, right? So this is going to be rho times our volume times our heat capacity. So now what are we returning? So we're going to return. We're returning an MP dot array, right? So we're returning an array, and in that array we want our we want our concentration first, because we have our concentration in the first of the vectors, right? And then we want our dt. Okay, next thing that we're going to move on to. So after that, all we need to do is do our solve function. So res dot equal, so we're doing the sp dot integrate dot solve IDP, right? Because this is an initial value problem. So what we want to do is we want to have our right hand side, and then we have our time. So our time is from 0 to t end, and then we have our initial guesses, right? So our initial guesses is going to be C at steady state and the temperature at steady state. And it's the temperature at steady state. Both of these are at steady state. Then we want to change our method to equal radu. And then our dense output is going to equal true. Okay, let's see. Okay, so I forgot to multiply this here. Yep, that works. Okay, so next thing that we have to do after this is we're going to make our plot. So the first thing we need to do is define our t-plot. So our time plot. So we need to do np.line space, and this is going to be from 0 to tn, right? And we want 100 increments to that. 100. Okay. Next thing after this, now we have our two graphs, right? So in our vector, we're having our concentration and our temperature. So we need to split those two graphs because we want to see two independent graphs from each other, so we can see that relationship, right? So we're going to have a C plot and then a temperature plot, right? And that's going to be equal to our res.solve, and then that's going to be based off of our t-plot. Okay, so now let's make our subplots. Rows equal 1, columns equal 2. Oh, yeah, columns equal 2, right? So we're going to have one row of graphs and then just 2 columns of graphs. So after this, now we can make our figure. So fig dot add underscore scatter. So our x is going to be our temperature, our time, right? Our t. Our y is going to equal our, the first plot is going to be our C plot, our concentration. It's going to be row 1, column 1. Name is going to equal the concentration. Next, we're going to add fig.add underscore scatter. X is equal to t-plot. And our y is going to be equal to our temperature plot. And our row is going to equal 1, and our column is going to equal 2, and the name is equal to time, temperature. Okay. Let's see what this is going to give us. So this is incorrect. Okay, so the mistake here was up here. It is, oh, I don't want that. Okay, so the mistake here was made as Tn is minus T, not T minus Tn, okay? So that was the problem with that code. So let's look at our two graphs here. So what's happening is our one over here, this is our concentration, and this is our temperature, right? So we have a high concentration of our Ca, and it's dropping, right? And so we can look over here. Our temperature is increasing. So as the temperature is increasing, our concentration is dropping, right? And see, it goes down pretty low, right? This is the highest the temperature gets, and this is the lowest the concentration gets. And then you're getting at these kind of similar peaks, right? These are like very similar peaks with each other. It's at the same height. So as it's going up in concentration, this is going down in temperature. And then it's converse, right? So when the temperature gets so high, the concentration of Ca is going lower. And when the temperature decreases, the concentration is going to increase. So that is the relationship between the concentration and the temperature in this.